Everyone, welcome to part 2 of chapter 5. Today we are going to talk about electron configurations. So we're going to look more about how these electrons are actually arranged in the atoms. So last time we started talking about atomic orbitals or energy levels, right? So we have these energy levels that we thought about as rungs on a ladder, right? Things could either be in the first energy level or they could be in the second energy level, but the electrons couldn't be in between, right? They couldn't be on that 1.5 energy levels. So these energy levels, each ring contains one or more sublevels. And these sublevels we call orbitals. And they are identified by the letters SPDF, or I like to think about SPDF. And I know that sounds weird, but just go with it. You'll remember it, SPDF. That's how we are going to remember the order of the orbitals. And the atomic orbitals are regions of space around the nucleus where there is a high probability of finding an electron. There's no guarantee that the electron's actually going to be there, and you'll get more into that in higher levels of Chem. But that's the technical definition. We're going to think of them as areas where the electrons exist. There are 4 different shapes of the orbitals, and those go with these letters. So we have the s orbital, which is a sphere, a p orbital, which looks like, they call them dumbbells, and there are actually 3 different shapes to these p orbitals. The d orbitals we call double dumbbells, and there are 5 different shapes. There's actually also a double dumbbell with a donut, which is great. And then the f orbitals look all kind of crazy down there. But there are 4 different shapes of these orbitals. You're not going to be asked to identify the shapes or draw the shapes. That's just more informational for you. But if you look at the drawing on the right, or the image on the right, you'll see in the first energy level, we have the 1s orbital. And then in the second energy level, we have the 2s orbital and the 2p orbital. And in the third energy level, we have the 3s orbital and the 3p orbital. So the number in the front is telling you which energy level it's in, right? This goes 1, 2, 3, and it would go 4, 5, 6, 7, right, going out. And then the letters tell you the shape of the orbital, and they're also going to tell you how many electrons can exist in those orbitals. We're going to get into that now. So within an energy level, we have the S sublevel, and that's the lowest in energy. The next highest is the P sublevel, then D, and then F. And so the order of increasing energy in the sublevels is SPDF, right? SPDF, SPDF, where the S is the lowest energy and the F is the highest energy. And the reason that this is important to know is that since the s orbital is the lowest in energy, it's going to get filled with electrons first, because electrons always want to be in the lowest energy level and the energy level that is closest to the nucleus. So the s orbital will get filled first, and then P and D and F in a given energy level. So we can look at the periodic table and we can see the different areas of the periodic table that correspond to the SPDF sublevels. And then we can sort of build the electron configurations by essentially reading the periodic table in order of increasing atomic number. So this is just another way that we can actually use the periodic table as a tool, right? I told you it's going to be like the world's greatest cheat sheet when you're done with this class. There's so much information on the periodic table, so we'll actually use it to read our electron configuration. So what I'd like you to do now is go find your periodic table. If you've got the one that we were talking about before, where we were making notes about the different groups, then that would be a good one to use. If not, I would print out a blank one and color it in, or at least circle it as SPDF, so you know where the SPDF blocks are. This is going to be really helpful as we start making these electron configurations before you get kind of used to them. You'll notice, though, helium normally sits here. Helium is a member of the S block, so it's kind of got temporarily moved over there, just as a heads up. So pause, make these notes on a periodic table. It will be really helpful to you, or you could even print this out if you want, but it doesn't have any elements on it. So I would recommend find a periodic table, color it in, or make some kind of notes so that you have this as you're learning to write your electron configurations. Here's another way of looking at it, right? You could just outline it, SPDF, whatever is the easiest for you to read. This is usually how I would do it, so I can still see the elements. So if we're looking at the S block includes hydrogen, right, which would be here, and helium, and then all of the elements under those, right? So it's got the alkali metals and the alkaline earth metals. This would be group 1A, and this is group 2A, except for, right, like I said, helium has joined group 2A for now. Elements in the S block have their electrons in the S orbital, okay? And the way that we can recognize their electron configurations is their last configuration will end in like S1 or S2, and we'll see that more as we go forward. The P block consists of elements 3A through 8A, again, except for helium. Helium's going to exist in the S block. There are 6 P block elements in each period, 1, 2, 3, 4, 5, 6. And we have 3 p orbitals, like I mentioned before, and in each orbital, right, so I'm going to write this down, we have 3 p orbitals, and each orbital can hold 2 electrons. So if there are 2 electrons in each one of those p orbitals, we have a total of 6 electrons total in the p block, which you can see as 1, 2, 3, 4, 5, 6. If we go back to the S block for a minute, there is only 1 s orbital, and each orbital can hold 2 electrons. So there are total 2 electrons that can go in the s orbitals, and we can see that by 1, 2 across. For the D block is all of the transition metals. So when we have them, right, we have, this is the S block, and we've got the P block over here. The D block is in the middle, right, the transition metals, and we number them as 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, okay? They're not the A numbers. They would just get the regular numbers. They also have B numbers, but they're a little bit confusing. And when we number these, you'll notice, so this is the 4th energy level that the D block starts on, but this gets a 3D. So I would, on that periodic table that hopefully you've printed out or something, make yourself a little note in the corner here and go 3, 4, 5, 6. And that will help you remember that the D block starts on 3. So even though it's in the 4th period, right, the 4th row of the periodic table, this gets numbered 3, 4, 5, 6 instead of 4, 5, 6, 7. So it's always going to be 1 less than the period number. So while you're getting good at this, I would make these little numbers and put 3, 4, 5, 6 in these first transition metals. So that will cue you in, hey, the D block's numbered differently. I need to pay attention to that. The period numbers are going to go for the S block and the P block, okay? But the D block, like I said, is numbered differently, 3, 4, 5, 6, so make yourself a note. There are 5 D orbitals, okay? And so each one of the orbitals can hold 2 electrons, like I said before, and so we get a total of 10 electrons that can exist for D block elements, and we see that as 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So if you ever forget how many electrons can go in a given block, you can just count across and see how many elements are in that block. That will correspond to how many electrons we can put in that block, which is really cool. The F block is the elements that are down at the bottom of the periodic table. They usually get kind of pulled out and put at the bottom. That's actually an interesting thing. They don't really belong at the bottom. They actually kind of belong in between the S and the D block. We just put them at the bottom to save room on the piece of paper. It's really what it is. So they actually go kind of up in between the S and the D block for reals. But the F block, these elements, we haven't talked about them much. They are called intertransition elements or intertransition metals. And they are the F block. So there are 7 F orbitals, and each orbital can hold 2 electrons. So that means there are a total of 14 electrons for this F block. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So again, if you ever forget how many electrons can go for a given block, you can just count across and divide by 2 to get the number of orbitals, which is cool. We are not going to really do any electron configurations for these F block elements because they're a little bit tricky. We're pretty much going to stick to the S, P, and D. So, but what I want you to remember, right? So I keep telling you SPDF, and SPDF is odd. So we've got this whole summary here with SPDF, But the main thing that I want you to know is I keep saying SPDF, which is an odd thing to do. So these are the shapes of the orbitals. And then we can figure out the number of orbitals by remembering all of the odd numbers. Okay, so again, me saying SPDF is odd. And so that is, you're going to remember, this is the number of orbitals, and it's going to be all of the odd numbers. And remember, each orbital can hold 2 electrons. So if I multiply all of these by 2, then you can get the number of electrons in each of the orbitals. So, okay, I'm not as crazy as I sound, right? A SPDF is odd, which is how you're going to remember the number of orbitals. And then again, 2 electrons in each orbital. So you can remember 2, 6, 10, 14. This, though, writes it out a little bit more, right? In the S block, we have 1 orbital, and it can hold 2 electrons, right? Because, it's only got 1. So in the P block, we have 3 orbitals. Each one can hold 2 electrons, so we have 6 total. The D block has 5 orbitals. Each one can hold 2 electrons, so we get 10 total. F block has 7. Each one can hold 2 electrons, so we get 14 total. Or you can just remember SPDF is odd, so 1, 3, 5, 7 is the number of orbitals. 2, 6, 10, 14 will be the number of electrons. Go ahead and complete worksheet problems number 7 through 9. This will help get you some practice on figuring out how many electrons go in each one of the orbitals. Once you're done, go ahead and come back and we will continue on with the lecture. Okay, so we have 3 rules to follow when we are figuring out how to arrange our electrons in our atom. The first of these rules is the off-bow principle, and the off-bow principle states that electrons will occupy the orbitals of lowest energy first. So they will occupy the orbitals that are closest to the nucleus. So that will we'll see the numbers that are the lowest that get filled first. So the 1s will be occupied before the 2s, or the 2p will be occupied before the 3p. So the lower numbers will get filled first. They'll also fill the s orbital before the p orbital, before the d orbital, and so forth. Remember, SPDF tells us the order of the orbitals. The Pauli exclusion principle states that an atomic orbital may have at most 2 electrons. So that means that they can have 0, it can have 1, or it can have 2, but it can't have more than 2. And electrons in those orbitals will have opposite spins. One of them will be spin up, and the other one will be spin down. That doesn't mean a lot in this class, but it will in higher levels of chem because each electron has to have kind of its own address. So if one of the electrons is up, the other one has to be down so that we can tell them apart. And then we have Hund's rule, which says that every orbital in a subshell is singly occupied with 1 electron before any orbital is doubly occupied. So this means, like for a p orbital, there's going to be 3 p orbitals, and we will put 1 electron in each of those p orbitals before any of them get 2. And it says that all electrons in singly occupied orbitals will have the same spin. So if you have, say, 3 electrons, 1 in each of those p orbitals, then they will all be spin up, or they will all be spin down. So these are our rules for how we're going to fill in our orbitals. I don't need you to know which rule goes with which name, but I do need you to know how they are used when we're filling orbitals. So again, we're going to fill the lower numbered orbitals first because they're closer to the nucleus. So that 1s will get filled before the 2s, and the 2s will get filled before the 2p because of SPDF, right? And so remember that there are 2 electrons that are going to go in each orbital, and every pair of electrons occupies an orbital. And again, we're going to put 1 electron in each before any get 2. So this picture is in your book, and this tells you the order of the orbitals. For the most part, they're going to go in order, 1, 2, 3, 4, 5, 6, 7, but there are some exceptions. Like you'll see the 4s is filled before the 3d. So they don't always go in order. So you can memorize this if you'd like, but it's easier to learn how to read the periodic table. We spend a lot of information, or a lot of time in this class looking to see how the periodic table is, the world's greatest cheat sheet. So that is going to be one of the things that I'll show you. The periodic table tells us how to fill in our orbitals. So here you go. Let's do oxygen, for example. So if we find oxygen here, Oxygen is atomic number 8, which means it has 8 protons, but that also means that it has 8 electrons. Okay, so we're going to use 8 electrons to fill in our orbitals. Now, if you'll recall, this is the S block, right, with helium. This is our P block. And then in the middle here, we have our D block. And then down here, this is our F. Okay, and again, we're not really going to do much with F. So the way that we're going to do this is we are going to read our periodic table. On yours, there should be numbers down the side. 1, 2, 3, 4, 5, 6, 7. And I told you to put little numbers here, 3, 4, 5, 6 for the D block. Okay, and so what we're going to do, we're always going to start in the top left like we are reading a book. You always start in the top left of your book and read across to the right. Right, so we're going to go like this on our periodic table. Okay, until we get to oxygen. So starting in the top left, we have our 1, right? We're in the first row, right? The first period, and we hit the S block first. And we look and we see oxygen is not in the 1S, right? Oxygen does not exist here. So we're going to put 1S down here at the bottom, and we're going to keep going. There's nothing else in this first row, right? Because helium is a member of the S block. So there's nothing else in the first row, so we'll go to the second row, and we'll look at the 2S. Now, oxygen, again, is not in the 2S, so I'm going to write the 2S down, and I'm going to keep going. Then we're going to keep going across the second period, and we hit the P block. And again, that's in the second period, and P block, so we're going to put down 2P, and we see oxygen is in this 2P. So we're going to write down 2P and stop. Okay, so we're going to write down the order of all of the orbitals. So it wasn't in the 1S, it wasn't in the 2S, but it is in the 2P, so we write it down and stop. So we're going to write all of the orbitals that come before oxygen. Now, we need to remember SPDF, right? And me saying SPDF over and over is odd. So that's how we're going to remember 1, 3, 5, 7. So in every S orbital, we have 1 sublevel, and we have, there's another 2S, and then for P, we have 3 orbitals. So we go 1, 2, 3. Okay, now we have 8 electrons to use in this orbital diagram. So we're going to start at the bottom because we have to fill in the lowest energy level first. So we're going to fill in the 1S before the 2S and so on. Now we have to fill up the 1S completely before we can move to the 2S, then we'll fill up the 2S completely before we can move to the 2P. So we'll go 1, 2. So each of those is like a half arrow. A half arrow means 1 electron in chemistry. So we go 1, 2, 3, 4, right? And you'll notice my electrons have opposite spins in these orbitals. And now when I get to the P orbital, remember, I have to put 1 electron in each before any of them get 2. So we're going to go 5, 6, 7, 8. Okay, so I filled up the 1S before I went to the 2S. I filled up the 2S before I went to the 2P. And for the 2P, I put 1 electron in each orbital before any of them got 2. And then I can only use 8 electrons because that's how many oxygen has. So this is the orbital diagram for oxygen. Let's try chlorine. So again, this is the S, right? S, we have P. Remember that helium's a member of the S block. And then we have D in the middle here and F down here. So 1, 2, 3, 4, 5, 6, 7, 3, 4, 5, 6 here. Okay, so we're going to go and we're going to try and find chlorine. So again, we're going to start in the top left. And first thing we come to is the 1s orbital. That's including helium. Chlorine is not in the 1s, so we're going to write down 1s and we're going to move on. So that's the first row is done, 1s. So then we come here, right, to the second period, and we get to the 2s. Chlorine is not in the 2s, so I'm going to write it down, and I'm going to move on. Then we keep going, and we hit the 2p. So that's this one here. Chlorine is not in the 2p. So I'm going to write it down and keep going. So now there's nothing else left in the second row, so now we go on to the third period. Chlorine is not in the 3s, so we write it down and we keep going. And then we hit the 3p over here, and chlorine is in the 3p, so we write down 3p and stop. Again, we're going to remember that SPDF is odd, right? 1, 3, 5, 7. So for every S, we get 1 orbital, and for every P, we get 3. Now, chlorine is atomic number 17, which means that it has 17 protons, and it also means that since it's neutral, it has 17 electrons. So we have 17 electrons to use. We're going to start with the 1s, and then go to the 2s, and so on. Watch the order that I fill in the orbitals, especially when I hit a p sublevel. So we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. So you'll notice when I hit a p orbital, I put 1 electron in each of the orbitals before any of them get 2. And I fill it up completely before moving on to the next energy level. So you need to fill it up like this every single time. Let's try another one. This is arsenic. So arsenic is here. So we're going to do the exact same thing that we've been doing. This one just has a little bit of a trick to it. So here's our S block. And remember, helium goes in it. Then we have our P and our D in the middle here and the F. Okay, so again, 1, 2, 3, 4, 5, 6, 7, 3, 4, 5, 6. Okay, so we're looking for arsenic. Arsenic, we start in the 1s. Arsenic is not in the 1s, so we write it down and we keep going. That's the first period is now done, so we'll go to the second period. Arsenic is not in the 2s. So we write it down and we keep going. Then we hit the 2p. Arsenic is not in the 2p. So we write it down. We keep going. Arsenic is not in the 3s. So we write it down and we keep going. Arsenic is not in the 3p. So we write it down, keep going. Arsenic is not in the 4s. So we write it down and keep going. And now we hit this D block here. So the D block we haven't encountered yet, right? The D block is numbered differently. Remember this number that I wrote here? That is a 3. So even though it's in the 4th period, this is 3D. So after 4S comes 3D. Okay? So don't get tripped up there. Down here I've written the D and F blocks are numbered differently. We're not going to do anything with the F block, but if you did, these are numbered 4, 5. Okay, but the D block you need to know, it's numbered differently. So it go 4S, right? 4S, and then this is 3D. And then we're going to get back to the P block. The P block goes with these numbers down the side. So after 3D comes 4P. So we go back to numbering just like the number of the period. The only one that's different is the D block. Okay, so even though it's in the 4th period, this is 3D. Okay, and then we'll go back to 4P, and then arsenic is in the 4P. So we write that down, and then we stop, because we have found arsenic. So then we remember SPDF is odd, so we go 1, 3, 5, 7. So for every s orbital, we get 1, right, 1 orbital. We have 3 p orbitals. And then we have 5 d orbitals. So now we'll go through and we see how many electrons arsenic has. It has, it's atomic number 33, which means it has 33 protons and 33 electrons. So again, we're going to start at the bottom, and then we're going to fill up each orbital before moving on to the next. When we hit these, they're called degenerate orbitals, like the p orbitals, where we have 3 with the same amount of energy. We'll put 1 electron in each before any get 2. So we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33. There you go. Arsenic is done. So go ahead and find your Chapter 4 lecture worksheet problem. Chapter 5 lecture worksheet problem, and practice these problems. We've got some orbital diagrams that you get to work on. Once you're done, come back and we will continue on. Okay, so we've learned how to do what's called orbital diagrams or orbital notation. So we'll do this again real quick for aluminum, just to make sure we're all on the same page. Aluminum is here. So we have the S and the P, right? Helium's a member of the S. Then we have the D in the middle here and the F down at the bottom. So if we do aluminum, which hopefully we can all do by now, aluminum is not in the 1s, right? So we write down 1s and we keep going. Nothing else in the first energy level. So then we go to the second. It's not in the 2s. So we write it down and keep going. It's not in the 2p. Write it down, keep going. Not in the 3s. So we write it down and keep going. And then we hit aluminum is in the 3p. And then we do SPDF, right? SPDF, 1, 3, 5, 7. And we go, okay, all of the S's have 1 orbital, P's have 3, and we're good to go. Aluminum is atomic number 13, which means it has 13 protons, and it also has 13 electrons. And so we'll fill it in starting at the bottom. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay, so some of these longer ones, like when we did arsenic, you'll start to notice that they're starting to take up a lot of space, and they take a long time to write out. And so chemists thought there's got to be a better way, right? And you're right, there is. There's a way that's much shorter. And so this is called the electron configuration. And the way that we do the electron configuration is we're still going to write out the order of the orbitals, but instead of drawing all of these lines and arrows, we're going to use superscripts to say how many electrons are in each one of those orbitals. So in the 1s, there are 2 electrons. In the 2s, there are 2 electrons. In the 2p, there are 6 electrons. In the 3s, there are 2 electrons, and in the 3p, there's 1. And that's much easier and much faster. And so you're like, well, okay, how do I write the electron configuration, though, if I didn't do the orbital diagram first? Now I'm doing double the work. Well, not quite. What we're going to do is I'm going to show you, right? Remember SPDF 1, 3, 5, 7? We also had the next row, 2, 6, 10, 14. That told you how many electrons were in each one of those orbitals. So we're still going to write the order of the orbitals, right? The 1s came, and then the 2s, and then the 2p, right? Just like we were doing before. But if we pass an orbital, like how we passed the 1s, the 2s, the 2p, the 3s, right? If we pass an orbital, we are going to assume that it's full, right? Because if you look, all of the orbitals that were not the one where aluminum is, they were all full. And so we can use this 2, 6, 10, 14 to be our superscripts so that we can, not have to count all of these electrons over and over again. So I'll show you how this works. This is just a little recap here, right? We use electron configurations to tell us the placement of electrons in the atoms. Again, we're going to write the lowest energy sublevel first, and then we're going to go on to ones with increasing energies. And then the number of electrons in each level is written as a superscript. So this is for carbon. And if we look at carbon, we'll just pop over here again. Carbon is here. So carbon was not in the 1s. So we write down 1s, and we know that the 1s then must be full, so it's going to get a 2 from up here. And then carbon is not in the 2s. I know it's getting hard to see, but carbon's not in the 2s, so we assume that it's full. So again, it's an s orbital, so it's going to get a 2. Carbon is, though, in this 2p. So carbon is in the 2p, so we write down 2p, and it's the second one in the 2p. So it's going to get a 2. Okay, you're going to write like how far into the p block it is. So that would be for carbon. So that's why you'll see 1s2, 2s2, 2p2. That's how we read it. 1s2, 2s2, 2p2. Let's try some more. So this is chlorine. So if we look at chlorine, right? Oh, actually, we did chlorine, right? Way back here. Let's go back. Here's chlorine, right? We'll use this one again. So chlorine, if we were going to do the electron configuration, we have chlorine is not in the 1s, right? So we write down 1s, and we move on. And remember, SPDF 1, 3, 5, 7, 2, 6, 10, 14. We've just multiplied each one of those numbers by 2 because 2 electrons can go in each one of those orbitals. So chlorine's not in the 1s, so we assume that it's full, so it gets a 2. Chlorine is not in the 2s, so we assume that it's full, and it gets a 2. Chlorine is not in the 2p over here, so we assume that it's full. It gets a 6, right here, 6. Chlorine is not in the 3s, so we assume that it's full. It gets a 2. And then chlorine is in the 3p, though. And again, we're going to count over how many chlorine is. 1, 2, 3, 4, 5. It's the 5th one in that p block, so it gets 3p5. So you'll see, right, either way, we have 17 electrons. So you could write it as this orbital diagram here, or you can write it as the electron configuration here. And if you went through and added up all the subscripts, 2, 4, right, 10, 12, 17, right, it's still going to equal 17 electrons either way that you write it. And you'll see that the electron configuration is much faster to write after a while, and it fits better on a piece of paper. So that's why we're seeing this one here. Okay, so again, always just look for it in order, right? In period 1, we had that 1s, and it wasn't in the 1s. It wasn't in the 2s. It wasn't in the 2p. It wasn't in the 3s, but it was in the 3p. So we count, it's the 5th one over in the 3p, so we get 3p5. Let's try another one. So here's lithium. Okay, so lithium is not in the 1s, right? So up here, it's not in the 1s, so we write 1s2, because remember, SPDF 1, 3, 5, 7, and we multiply all those by 2, we get 2, 6, 10, 14. So it's not in the 1s, so 1s gets a 2. It is, though, in the 2s, so we write down 2s, and it's the first one in the 2s, so we have 2s1. That's it. We're done with sodium, or with lithium. Now we're going to do sodium. So sodium is not in the 1s, so we write down 1s2, right, because it's full. We go then here, it is not, sodium is not in the 2s, sodium's down here, not in the 2s, so we write down 2s2, because the s orbital is full. Then we keep going across, we hit the 2p, sodium is not in the 2p, so the 2p is full, so it gets a 6. Sodium is, though, in the 3s, so we write down 3s, and it is the first one in the 3s, so we write 3s1. Now we can do bromine. Bromine's down here. Okay, so bromine, not in the 1s, so we get 1s2. Not in the 2s, so we get 2s2. Not in the 2p, so we get 2p6. Not in the 3s, so we get 3s2. Not in the 3p, so we have 3p6. Not in the 4s, so we have 4s2. Now remember, the D block is numbered differently. This is 3, 4, 5, 6. So this is 3D. Bromine is not in the 3D, so we write 3D, and we haven't hit a D block before, but D is 10. And then it is in the 4P though, right? Remember when we switch back to the P, we switch back to the numbering system we had going on before. So this is 4P, and it is the 5th one in the 4P, so we write 4P5. If you ever forget the SPDF, the 1, 3, 5, 7, right? Me saying SPDF is odd, so we remember 1, 3, 5, 7, and then you multiply all those by 2 to get 2, 6, 10, 14. If you ever forget the 2, 6, 10, 14, you can honestly just count across, right? So say we forgot how many was supposed to go for the D block. We would count how many elements across the D block is. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And that's why D block here gets 10. Same thing for the P. 1, 2, 3, 4, 5, 6. That's why the P block here has 6. So if you forget those numbers, you can just count across the blocks, and that will tell you how many electrons can go in each one of those sublevels. All right, go ahead and find your chapter lecture worksheet and complete problems 11 and 12 to get some practice on electron configurations. Once you're done, come back and we will keep going. Okay, Our last topic for today is abbreviated electron configurations. And we use these abbreviated electron configurations as an even shorter method because as you'll see, right, like bromine started to get a little long. And if we were going to do some really big elements, right, with a lot of electrons, we would be writing these electron configurations for a while. So again, chemists were like, there's got to be a better way. And there is this abbreviated electron configuration. So we make it even shorter. You're going to find the last noble gas that came before the element, and you're going to put it in parentheses. And that noble gas is going to act like a placeholder. And the noble gas is going to say, okay, this element has all of the electrons that say helium has, plus a few more. So it's like start at helium and then write the electron configuration for your element. So we're going to go backwards to find the noble gas that came before it. So like lithium, if you go backwards and you find the noble gas that came before lithium, that would be helium. So we put helium in brackets, and then we take away all of the electrons that belong to helium, and we write the electron configuration for lithium that comes after helium. Okay, this will make more sense in some examples. So let's try this. So magnesium. So here's magnesium. We find the noble gas that came before magnesium, so we go backwards. So 12, 11, 10 is neon. So we're going to put neon in brackets, okay? And then we're going to write the electron configuration for magnesium that comes after neon. So instead of starting at the top left, we're going to start after neon. So we're going to start here, okay? So instead of going 1s2, 2s2, 2p6, right, all of those electrons belong to neon. So we can start with the 3s, and magnesium is in the 3s, and it's the second one in the 3s, so we get a 2. And we're done. Much shorter. Let's try oxygen. Oxygen's here, so we go backwards and we find the noble gas that came before it. So we go 8, 7, 6, 5, 4, 3, 2, we get to helium. Okay, so again, we're going to write the electron configuration for oxygen that comes after helium. So we don't start in the top left, we are going to start here. Okay, so it is not in the 2s, so we write down 2s2, and then we keep going, right, and we hit the P block over here, and it is in the P block. It's the fourth one, so we go 1, 2, 3, 4, right, fourth one. So again, much shorter. Let's try chromium. So chromium is down here. So again, we go backwards. We find the noble gas that came before chromium. So we go 24, 23, 22, 21, 20, 19, 18. We hit argon. So we put argon in brackets. And then we're going to write the electron configuration for chromium that comes after argon. So we're starting here. Argon is not in the 4s, so we write down 4s2. And so again, remember the D block is numbered differently, 3, 4, 5, 6. So it is in the 3D. And it is the 1, 2, 3, fourth one in the 3D. So we write down 3D4. And that's it. So these abbreviated electron configurations are a much shorter way of showing the electron configuration. They're much faster to write, and they don't take up as much space. So it's really, really cool. All right, go ahead and complete lecture worksheet problems number 13 through 16.